This is easy sum questions. This question mean is sum of remainders when divided by I using m. Now I am going to introduce how to solve this problem using an example. Let's take n equal 10 because n is greater than and equal to 1, less than and equal to 10 to the power 9. Next, let's take m equal 3 because m is greater than and equal to 1, less than and equal to 10 to the power 9. Take the remainders when 10 is divided by 3. Repeat the same step for all the other numbers and include these remainders in a set of named capital B. Finally, add all the elements in set capital B and this will give you the answer.
We are given an array A with n elements. Our goal is to calculate a result for all distinct pairs ij, where j is greater than I, using the formula ai plus aj over ai into aj. The flow operation ensures the result is rounded down to the nearest integer. For each test case, the cumulative sum t is the total of all pair values. For example, suppose that a equals 1, 2, 3. Identify all the pairs. The pair 1, 2, where a1 equals 1 and a2 equals 2, pair 1, 3, where a1 equals 1, a3 equals 3, and the pair 2, 3, where a2 equals 2 and a3 equals 3. Let's apply the formula. For 1, 2 pair, the formula gives us the result 1. For 1, 3, the formula gives us the result 1. For 2, 3, the formula gives us the result 0. Now let's sum the results. T equals 1 plus 1 plus 0 equals 2. So the constraints are T should be greater than or equal to 1 and less than or equal to 15, and N should be greater than or equal to 1 and less than or equal to 200,000. The values in A should always be greater than or equal to 1 and less than or equal to 10 to the power 9.
We use modular arithmetic, specifically modulo 100, to simplify the calculation and avoid handling extremely large numbers. The key method used here is modular experimentation by squaring, which efficiently computes I to the power n mod 100. After calculating each term in this form, we sum the results and again take modulo 100 to determine the final value. This approach ensures the accuracy and reduces computation difficulty. For example, if k is equal to 2, n is equal to 2, we compute 1 to the power 2 plus 2 to the power 2 mod 100, giving a result of 5. Similarly, if k is equal to 3 and n is equal to 3, 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 mod 100 equals 36. This method is effective even with the given constraint of large k and n.
First, we need to generate a sequence. Start with A0 equals 0, A1 equals C, where C is a constant we choose. Then we use formula AI plus 2 equals AI plus 1 plus AI mod m to calculate all terms up to 2n plus 2. This gives us a sequence we will work with. Next, we form vectors, starting with third term, group this sequence into consecutive pairs. For example, A2, A3, A4, A5, and so on. These pairs will become our vectors. Now we calculate scale product for each pair of consecutive vectors. The formula is, this is scale product equals x1 dot x2 plus y1 dot y2, where x1 y1 and x2 y2 are components of two vectors. Finally, collect all scalar products into a set. This ensures only unique values are stored. Count the size of this set and we can get the answer.
First, what is the sequence Tn equals n to the power k? It's a list of numbers where each term is calculated by raising n to the power k. For example, if k is equals 2, we get square numbers, which gives us 1, 4, 9, and so on. To find the sum of these terms, we calculated Sn equals T1 plus T2, adding up to Tn. For instance, if n equals 3 and k is equals to 2, the sum becomes 14. But what happens when n and k are really large? Numbers can get huge, making them hard to manage. That's where modulo 10 to the power 9 plus 7 comes in. Modulo help us keep numbers manageable. We only report the remainder when dividing Sn by 10 to the power 9 plus 7. For example, if Sn equals 1,000,000,009, dividing it by 10 to the power 9 plus 7 gives a remainder of 2. So instead of the huge number, we simply report 2. Think of it like saving coins in a piggy bank. Each day you add n to the power k coins. At the end, you calculate your total savings, but instead of reporting the total amount, you only tell how much is left after dividing by 10 to the power 9 plus 7. To summarize, calculate Sn equals 1 to the power k plus 2 to the power k plus 3 to the power k and adding up to n to the power k. Find the remainder of Sn divided by 10 to the power 9 plus 7.
Query 1. We start with a equals 1 and b equals 2 to compute gn as sequences like this. G equals 0, 1, 1, 3, and 5. Next, we calculate the coefficient Ci, which you can see, and using these, we compute S1 and S2 for different values of p, like when p equals 1 or p equals 2. From there, we compare S1P and S2P to count where S1P is greater than, equal to, or less than S2P. For instance, in this example, count 1 equals 0, count 2 equals 2, and count 3 equals 0. For query 2, take P equals 1, U equals 2, and V equals 2. Compute Gn, for example, G2 equals 1, then calculate Zi using the equation. Z2 plus 2p equals Zt plus 1 plus 2. Finally, calculate S using W and 5. Calculate from the problem's equation, substitute the values, and we get S equals 1.
Here's how it's worked. Let's imagine circle of children, each started with an initial number. The summation begins when a specific child at the number of the two children sitting beside them. The process moves clockwise, updating the number of each child sequentially. Once the last child is reached, the process goes back to the first child, maintaining the circular flow. The summation continues for a quantified number of rounds. Let's look at an example. Suppose there are 5 children and only one round with an initial number 10, 20, 30, 40, and 50. If the process is started with the child 1, the output becomes 80, 20, 30, 40, 50 as child 1 and the numbers from 2 child beside him. If it is started from the child 2, it changed 10, 60, 30, 40, 50, and so on, depending on which child initiate the process. This exercise demonstrates how simple rule can create complex pattern in data when combined with circular structures.
The problem involves counting how many valid matrix A and vectors B give exactly a solution to a modular linear conjugate system. The number of solutions depend on the rank of matrix A modular A prime number P and whether the system is consistent. The formula for the solution count P to the power n minus R, where n is the number of variable, R is the rank of A. To ensure exactly a solution, P to the power n minus R equal S, meaning log S must be an integer. If not, the test case fails. The process begins with determining valid configuration for A by computing its rank using Gaussian elimination modulo P. Next, each valid A is checked for consistency with B to ensure A dot X equals B, counting only configurations that result in a solution. Finally, all consumptions are carried out under modulo 10 to the power 9 plus 7 in the provided example. Zero constraints adjust the matrix A, altering its rank to meet the conditions for the desired number of solutions.
The problem involves calculating KPR sum by performing XOR operations between elements of list capital A and simple A with key K. Initially, KPR sum is set to 0. Then we loop through each pair of elements, array I and array J, where J greater than I. Perform the following. First, compute array I and array J. Second, XOR the results with K. Third, add these results to KPR sum. This process continues for all pairs ij where j greater than I. After all iterations, the final value of KPR sum is results. For example, if A equal 5, 3, 8, 6 and K equal 2, the final output after all XOR operations give the value for KPR sum. The key idea is not that XOR nullifies matching bits, which makes this a useful operation for certain security and error checking applications.
Now I'll explain how to solve a rational sum problem to determine its convergence. The general term of the expression 1 over n into n plus 1 is simplified using partial fractions, which will give us 1 over n minus 1 over n plus 1. Then, by substituting consecutive values for n, starting from n equals 1, then n equals 2, n equals 3, n equals 4, and so on, it is clear that all the terms cancel out, leaving only the first and the last terms in the series. This simplifies the series to give 1 minus 1 over n plus 1. To find the sum, we apply the limit as n approaches infinity. Since 1 over n plus 1 goes to 0, the series converges to 1. In conclusion, the series 1 over n into n plus 1 is a convergent series and its sum is 1.